So thank you everybody for staying. This is our last session for today. It's a recorded one. So as you can see by Dr. Bin Fan, and he will talk about simplified data preparation for machine learning. And let me play it.
From Alluxio, a company builds technology to bridge your analytics or AI computation with your data. Today, my topic is about how to leverage Alluxio to help data scientists and engineers to prepare data in a hybrid or multi-cloud environment for machine learning and analytics workloads. Apologize first for not being able to present and discuss with you in person. If you have any question after my talk, feel free to reach me out by the email below. Okay, now let's start. Motivate my talk. Let's first take a look at where the data world is today. Overall speaking, the amount of data, variety of the data, complexity of data for enterprises keeps increasing. The amount of data is exploding. Study shows that there are more than 2,500 petabytes of data created each day at the current pace, but that pace is only accelerating. Over the last 2 years, 90% of the data in the world was generated. The complexity to keep data accessible is also increasing. There are many different types of data today, varying from transactional data, behavioral data, IoT data, social data, communication data, and many other types. Some of this data is obviously more important and business critical than the others, but in any case, it needs to be stored somewhere. Inside enterprises, there is no doubt that insights from data will create differentiation. Every company will need to be a data company. So it comes down to how such a large amount of data with such a high complexity can be managed and made accessible from different teams and different projects across the organization. Let's look at the tools data scientists and engineers use to deal with the complexity in this data ecosystem. 10 years ago, we had very limited choices, and this is perhaps the only stack using Hadoop MapReduce as the programming paradigms and HDFS as a storage to serve a massive amount of data. But take a look at the data ecosystem today. On the computation side, we have MapReduce, Hive, Spark for ETL jobs. We have Presto, Spark SQL, or Hive for SQL analytics. And we have Caffe, TensorFlow, PyTorch for machine learning workloads. On the storage side, HDFS is no longer dominating, but we see more and more use of object stores, especially for public cloud storage like S3, GCS, Azure Blob Store. And many other hardware vendors also provide their own services similar to HDFS. So the ecosystem is fundamentally different, and we're seeing an explosion of different systems showing up in this stack. So this is the brief overview for Alluxio. Alluxio was originally a research project called TiCal from UC Berkeley and Lab, led by the PhD student, now Alluxio CTO Haoyuan Li. It was the open source project from very beginning, and we created this company to commercialize Alluxio as open source technology. This company was founded by top VCs like Hendricks and Harrods, and the goal is to build a data orchestration system to unify the data at memory speed in the cloud. And along the way, we're building this system and the company. There are different recognitions from different media. Because I mentioned this is open source technology, we are actually having a very fast growing open source community too. On GitHub, we have more than 1,000 contributors with 4,000 GitHub stars. The project itself is under Apache 2.0 license, which is very popular in the big data analytics space. We also have Slack channels. If you have any questions, feel free to join the Slack channel and raise your hands. And this is the source code hosted on GitHub. Alluxio as open source technology has been adopted and deployed in many leading companies all over the world. This page shows you different industry sectors and companies in each industry sector using Alluxio in their production use cases. And you can find many different big names in this page. Alluxio is also deployed at scale. We know the largest scale of the cluster is running at least thousands of nodes of Alluxio workers. So Alluxio has been battle tested in the production workloads to serve many different users. Okay, so much for the overview. Let's go to the technical details with the innovations Alluxio provides. This page shows you the data ecosystem and where Alluxio is in this data stack. On the upper side, you can see different computation frameworks, including Presto, Spark, MapReduce, TensorFlow, and many more. And on the bottom part, you see different physical data stores, including S3, Azure, Google Cloud Storage, HDFS, and many more. So Alluxio is in the middle of these two layers, the computation layer and also storage layer. So Alluxio is not computation or storage. Instead, we're adding a new layer to this data ecosystem, and we call this new layer data orchestration for the cloud. What it provides is that you can think it's an abstracted data file system, and providing the same data abstraction to different data application or data frameworks using their favorite APIs, including Java File System API, HDFS API, S3 API, POSIX, or REST APIs, based on their favorite APIs they want to use, but they are accessing the same data. And on the bottom part, Alluxio provides different drivers or connectors. So Alluxio can read or write the data from different physical data stores without even this is transparent to the application, without letting applications even be aware of these different physical stores or the configuration or the setup. So Alluxio, you can think it's a new layer to provide an abstraction for computation, and in this new layer, you can install different data policies and do some data optimization, including caching or some other optimizations to improve the performance. This slide explains the file system abstraction functionality provided by Alluxio with a little bit more details. So you can think Alluxio provides a common interface across different applications, frameworks, and it can be the HDFS compatible interface. In this way, you just simply change the file address from HDFS : / into Alluxio : //. And because Alluxio client is fully compatible with HDFS interface, the applications or the frameworks does not need to do any code change, but being able to access data from Alluxio HDFS API already. We also provide some other interfaces like the POSIX API as mentioned. So in this case, legacy workloads or the machine learning workloads like TensorFlow, they can just use the POSIX API to access the same file system. In this way, the cloud storage or some other physical storage behind Alluxio can be hidden to applications, and this is transparent and brings in a lot of flexibility. The next feature, enabling the storage unification, and we call this the unified namespace, and which enables effective data management across different storage. So in the middle, you can think Alluxio is providing this blue, which is the logical Alluxio namespace to different applications. And underneath, this logical namespace can be backed by one or multiple different storage, physical storage. And Alluxio is merging their namespace into a logical namespace and hiding all this implementation, concrete implementation to applications. So as a file system, we have a directory structure much like the Unix, but instead of mounting hard disks into directories, in here we're just mounting different external and maybe distributed storage or storage services into the same logical namespace. It's pretty much like how you do this for the hard drives into your local file system. The third enabling innovation for Alluxio is what we call the caching, which solves the locality problem if your data is stored in a location far away from your data application. So in this way, by using Alluxio to connect your data, by deploying Alluxio co-located or close enough to your application and connecting to the storage, you will be able to store the hot data into your Alluxio space and make it closer or even co-located with application without needing to access data repeatedly from over the network. And Alluxio can automatically promote and demote data based on the usage. So you can, if the data is in Alluxio and not being used for a while, and this can be evicted out, and Alluxio can next time when you access the same data, Alluxio can transparently retrieve the same data for you from the remote data store without letting the applications aware. And also Alluxio can be allocated with different storage resources, including RAM disk, including SSD, including hard disk. And you can use Alluxio as a black box to manage the storage resource inside. In this caching layer, you can also add some data policies to ping data in this Alluxio space, or you can set a TTL for data to be evicted after a certain time. So it's a very powerful tool it's a very powerful feature for Alluxio to improve the performance for Spark, TensorFlow, or Hive, this kind of different computation when they want to read remote data or from multiple different clouds. Another innovation is the server-side API translation. Our file system has a modular framework that allows us and the community developers to create a new northbound interfaces to compute technologies and southbound interfaces to understore technologies. These modules translate interface-specific commands to and from our internal API. As a result, this gives Alluxio the ability to easily create a new pathway from one interface to another. For example, if a developer wants to develop in HDFS, but his storage is in Ceph, Google, or NFS, Alluxio will handle the translation of the requests and response. Note that this translation happens on the server side. That means you don't have to update your client side, which can be very hard or challenging in many production environments, but just making the configuration change on the server side. So one interesting case is you can even mount multiple different HDFS connector with different versions into the same logical namespace that they share a same HDFS or some other interface to the applications, but underneath, different paths are backed by different HDFS versions, even they are not compatible with each other. This slide shows how to use different computation frameworks to access Alluxio, including Spark, Presto, Barsh, TensorFlow, and Java. In Spark, let's first take a look at Spark and Presto because they can both use HDFS client API to read and write data. And in this case, because Alluxio is providing a HDFS compatible API, you can simply replace the scheme in the URL from HDFS : / to Alluxio : / and Spark and Presto applications will be able to read Alluxio in that way. If you mount Alluxio using the Fuse API, using the Fuse integration, and Alluxio can be treated as a local file system folder, and you can continue to use your familiar Linux commands or 20 Linux TensorFlow or this kind of machine learning frameworks to read and write data from Alluxio, but pretending they're just accessing a local file system folder. In many Java applications, if you want to access the full feature for Alluxio, you can also bring in the Alluxio file system API, which provides all the functionalities in Alluxio. Okay, now let's talk about Alluxio POSIX API. And this API allows users to access remote data just like a local storage. Alluxio provides a fuse-based POSIX interface, so you can mount Alluxio and expose it as a local file system on macOS or Linux. Applications can interact with the data in the Alluxio file system using the standard POSIX APIs like a read, write, open, without any customized client integration. But there's one caveat. Alluxio itself is largely the same as HDFS in terms of semantics. So we provide the right ones, read many file system semantics. You can write a new file into Alluxio namespace, but once this file is closed, you can no longer update this file. So that means even if the Alluxio service is mounted into the local file system through the fuse-based POSIX API, the mounted file system will not support all the POSIX workloads if it requires in-place update. So this shows you basically the stack of using Alluxio POSIX file system API to serve machine learning workloads, including Caffe or TensorFlow or PyTorch. So essentially, Alluxio is connecting to the Android storage system, including S3, Azure, Google Cloud Storage, but provide a unified data abstraction through the POSIX file system API. And this will expose the data as a local files in local folder to this machine learning workload frameworks. And this figure shows what it looks like. Essentially, Alluxio as a logical file system is shown as a local folder in your local file system, and the different folders inside Alluxio can be backed by different Android storage, and this is actually transparent to applications, transparent to users, and you get the feeling that you're just accessing a local file, but instead this file can be stored in a remote Alluxio worker or in a remote persistent storage, but you get a feeling like you're accessing the file locally. Because Alluxio also provides the data caching, so even the data is from the remote storage, Alluxio can cache this closer to the applications. And here we show you some benchmark results by running AlexNet using TensorFlow, and see the training throughput by reading from S3 directly or reading from Alluxio with data cached originally in S3 but data cached in Alluxio. As you can see in this figure, we have very similar performance as Alluxio. Using Alluxio in this stack, it provides a very similar performance as running the AlexNet training throughput with reading from local file directly. And if you want to get more details, you can just visit the blog with the address list here. Now let's show the example workflow to run machine learning workloads like TensorFlow on Alluxio. First, you can launch Alluxio instance by deploying Alluxio locally. You can just run Alluxio start.sh with the local as the argument and -f indicating we're formatting this new instance. By running this first step, you can then mount a cloud storage, in this case S3 bucket, into Alluxio namespace. Okay, you can just run the following command, and this will just put a S3 bucket, which is a public bucket already, into the Alluxio namespace under the directory called training data. If the mount command is successful, you will see a message like mounted S3 with the bucket name and followed by the Alluxio path. You can run the following command to check out the files if they are successfully mounted by running Alluxio fsls with the Alluxio namespace directory, which is training data. And you will see, you're supposed to see the files in the bucket now is shown as the logical file in the Alluxio namespace. And you can also mount Alluxio namespace into local file system at this step by running Alluxio fuse script. And you see the mount /mount /Alluxio, it's the local file system directory, and the /training data is the Alluxio path. So by running this command, this will mount a Alluxio service with the directory into this local directory. And from now on, you can double check the files are the same file in the S3 bucket can be seen in multiple different ways. For example, you can use the AWS script, AWS S3 LS script to check this object in the bucket. Or because Alluxio, this bucket is mounted into Alluxio space, you can run bin/Alluxio to check the same file. But in the Alluxio logical namespace, you should see the same file name with same size, with same metadata. And now because the Alluxio service is also mounted into the local folder, you can double check this information by running a local Linux ls command and see the same file in the mount /mnt/Alluxio direct local folder. Because the file has been mounted successfully into the local folders through Alluxio, you can run the training script. You can using the training TensorFlow training script, and you can stop the mount and Alluxio service using this command. If you want to find more details about having these workloads, you can check out the URL below. So what's the benefit of doing this? Essentially, you can use Alluxio to connect multiple different remote storage. Plus, you can use Alluxio as the way to cache this data. So in case you need to run this multiple times or in multiple different applications, then using the same data, you will see a speed up accessing the data without manually copying the data from the remote storage to your local machine to simplify your steps to prepare the data. In the next few slides, I want to show an example workflow to run Spark workloads on Alluxio. Let us start a Spark shell first. Note that in order to be able to access Alluxio as a file system in Spark shell, you need to append the path to Alluxio client jar file to the Spark shell's driver class path. Otherwise, the file system address starting with Alluxio column / will not be able to be recognized. Entering the Spark shell, we can read RDDs from Alluxio exactly as how we read RDDs from other systems like HDFS or S3 using Spark, with the URL scheme replaced by Alluxio. Similarly, when writing RDDs to Alluxio, simply replacing the scheme in the URL and run save as text file. To use data frame in Spark served by Alluxio, simply store the Parquet files in Alluxio file system, and then load from or dump to Alluxio file system the data frame using the data frame API. Again, the usage is the same as other file systems as like HDFS or S3, and you can achieve this without any code change. Now let's take a look when to use Alluxio, and in different use cases, what are the different benefits you can get in different scenarios. In the first scenario, assume you have a HDFS as a data lake enabling co-located Hive workloads and MapReduce workloads. They're running in the same data center and reading data locally. Now you want to set up a satellite cluster for performance isolation or resource isolation. You want this satellite cluster still able to access the main data lake HDFS. So in this case, we see a lot use cases, user using Alluxio as the caching layer for this satellite cluster to enable efficient data fetch in this satellite cluster against the Hadoop HDFS data lake. Because Alluxio can cache the data, if you access the working set repeatedly, then Alluxio can save the bandwidth to read from HDFS repeatedly, but also offload the RPC pressure from Alluxio from HDFS name node. Another use case we see a lot is to use Alluxio as a single cloud storage caching layer. So if you're running your analytics workloads in the public cloud in the stack, using Spark to access Spark or some other analytics tools to access S3 or similar cloud storage sometimes can be inefficient due to multiple reasons listed here. First, the performance can be variable for S3, and the consistent query SLO can be hard to achieve. Metadata on object store can be expensive because object store has fundamental difference in the design and the implementation compared to file system. The egress costs may add up, and also the eventual consistency is seen a lot, causing troubles for users to query. If you use Alluxio as a caching layer on top of S3 or similar cloud object store, then the applications can see a familiar distributed file system semantics with improved performance to achieve consistent SLA. Another use case we call the zero copy bursting with hybrid cloud. Essentially, you're running a workload in the public cloud, but the source of truth of data is in the on-premise data warehouse. If you run this in this setup, reading data repeatedly through the network to get data from the on-premise data warehouse to public cloud can be expensive and inefficient. Instead, you can running Alluxio co-located with your applications or computations in the public cloud, and in this way, Alluxio can intelligently just cache the data without running this CP explicitly from the Hadoop HDFS to the cloud, and on-demand cache the data, the working set. Well, the last case is we see a lot is people are moving away from HDFS to object store. So running Alluxio co-located with the computation framework and backed by object store can bridge up the performance gap between running a co-located distributed file system versus reading data from remote separate or remote object store. In the last few slides, I want to share some use cases in real environment, in real production environment. So the first use case is in JD.com that Alluxio is used to co-locate with Presto and Spark as a caching layer to avoid reading data repeatedly from the HDFS cluster. In this case, the team can run additional workloads without taxing the existing HDFS cluster and with 10x performance gain, according to the observation they found. Another use case is to run the Presto workloads in a single cloud environment in Walmart. So essentially, Alluxio provides an intelligent distributed caching layer for object store, in this case, the Google Cloud, and they are using Presto to query Alluxio instead of querying the object store directly for higher performance queries and more consistent performance. So this is the last slide. Alluxio provides the unified data access layer for big data and ML workloads. If you want to use the ML machine learning frameworks to access local folder, but backed by remote data, you can use Alluxio based on the fuse integration and presenting the remote data to the local and without explicit data copying, and simplify the data preparation phase. If you want to try out Alluxio, this is the link you can use. And thank you for your time. I'm happy to have any questions. You can send me questions through emails. And hope you've had a great day.